Hello and welcome to Lab 15, Glacial Geomorphology. This video is provided for you as instructional support for this lab, as well as to give you some tips, tricks, and some little hints to try to just get through this a little bit easier on your own. These videos are going to be very helpful, not just for the fact that you're getting the lab explained to, but in case you need to go back and review it later on in the term, you're able to go back and see kind of the steps taken in order to complete these labs. Now, as we can see, the objectives of this lab are to describe the processes that cause glaciers to advance and retreat, to analyze glacial mass balance data, to identify erosional and depositional glacial features, and to explain how glacial melting can affect sea level rise. We'll be utilizing not just some old-fashioned hand drawings, but we'll also be utilizing some great resources to visualize sea level change throughout the United States. Well, that being said, let's start Lab 15. So before we begin with Part A, it's just really important for us to know, especially as you learn in your lecture courses, just how much ice was there in North America. During the Pleistocene, which was between about 2.6 million and about 10,000 years ago, at its maximum, the extent came as far south as northern Los Angeles County and covered over 13 million square kilometers of California, reaching thicknesses of up to 3 meters in depth. So we're talking about a tremendous, almost unfathomable amount of ice that would have been carving our landscape. So when we speak of glaciers, we're really talking about really large amounts of accumulated snow and ice that we're able to pluck and carve and abrade and change our landscapes that we get to enjoy today. Now, Part A is talking about those glacial processes that I just mentioned. So as we move forward through the lab, you'll learn more that, as water freezes, it expands. And so what we are able to observe is that we have different volumes of ice that we can identify. We have what's considered continental glaciers or ice sheets. We have alpine glaciers, valley glaciers. We're able to see that depending on the region in which that ice was accumulating, that we could then observe essentially the name that is given to it. So when I think of the alpine glaciers, I think of the Alps, the mountain peaks. When we think of continental glaciers, we think of large, vast areas covered by tremendous amounts of thick ice. So this diagram below, figure 18.1, known as the cryosphere, is showing essentially all the snow, permafrost, sea ice, ice shelves, ice sheets, and glaciers throughout the world. And we can see some explanation has been provided for you while talking about how this projection of the map is trying to express the regions at which ice has accumulated. Remember that glaciers and ice are the accumulation of snow over decades and decades and decades. So as we move forward to this next part, we can see that question 1 is asking you to reference that diagram before to identify where are alpine glaciers found. Then moving forward, we learn about the 2 great continental glaciers of Antarctica and Greenland, shown in pink on that figure. So that being said, we're able to learn and measure the rate in which glaciers are advancing and retreating, which has become a very hot topic that's being observed today due to climate change. So the question here says, speaking of large features, one of the fastest moving glaciers is the Jakobshavn Glacier in Greenland. It moves at a rate of about 12.8 to 16.4 kilometers per year. So question 2 is asking you to do a little bit of math. Utilizing an average rate of 14 kilometers per year, it's asking how fast is it moving per day? So once you solve that, you'll move and learn a little bit more about it. I've provided a QR code here for question 3, which is an abbreviated Chasing Ice video. Chasing Ice is a documentary of which really I think it's quite fascinating. It's a guy who was a photographer for National Geographic, and he made the argument that scientists and scientific reports produce so many graphs and charts and tables trying to explain how ice is becoming limited on Earth's surface, and that we are losing tremendous amounts of glacial ice, and then at that point it melts and goes into the oceans. In some areas it's even deflating, meaning that the surface area might be increasing, but it's actually decreasing in depth. So doing what he does best, which is taking photos, he set up a lot of stop motion cameras throughout these large areas that have ice and over very long periods of time, and recorded day by day, minute by minute, the change that could be observed, and he was able to capture the world's largest calving event ever seen. What is a calving event? Well, that means the glacial ice, when it breaks off and turns into an iceberg, that's called a calving event, and he was able to record that. So this is having you watch that short part of this very long TED Talk, which is also then part of a full documentary, and it's asking you to just kind of, observe the video and interpret that data and answer a few questions based on that. So that being said, I just think that that's really a great resource. As we move forward, we learn about a new diagram, which is figure 18.2, which is a cross-sectional view of the zones of ablation and accumulation. So these are some new terms in which we have. So I want to kind of speak to that. We have what's considered the equilibrium line, which is really the melt line. That is the line in which separates the ice from gains and losses. The zone of ablation is the zone of losses. The zone of accumulation is the zone of gains. So what ends up happening is that high up in the mountains, rain, may occur, turns into snow, that snow compacts, and under its own weight, it begins to push downward this large accumulation of ice. So it then advances. Well, as it advances, if it goes beyond that equilibrium line, the ice begins to melt in the zone of ablation and it melts back. So you kind of have this cycle, and it's normal for glaciers to melt back and to have a zone of ablation, especially during the summer, but it's also normal for glaciers to advance during the winter, and so you're supposed to have this healthy gains and loss type situation. But unfortunately, and many times and more observed recently, the losses are exceeding the annual gains, and so we see full-on advancement. So it says here for figure 18.3 shows the balance from data of 1976 to 2018 for 3 alpine glaciers, so of which I'm going to now change the page so we can see this table here. And what it's having you do is answer some specific questions about that graph. So you can see here, it says refer to 18.3. What is the overall trend in the mass balance for these 3 glaciers? And also, using your critical thinking skills, when looking at a mass balance data, why would it be important to analyze data over long periods of time? So why is it important for us to look at data over long periods of time versus just more recent or just historical? Why is it important to include all of that data? And if just for fun, you might want to Google where these glaciers are, so you just kind of get an idea as to what we're looking at when we speak of just spatial studies. Now, the next figure, 18.4, shows the cumulative mass balance loss for alpine glaciers worldwide. And then you're going to be able to take some of that data. As we can see, it's been itemized here for you in the lab. And here we can see the graph. And we also can observe that between 1980 to 2015 and beyond, we have seen a progressional decrease in cumulative glacial ice mass. So it's asking you to really evaluate this graph and what is your overall observance. So like I said, what's really interesting about just this data in particular is that many people will agree that in some regions around the world, glacial ice is advancing more recently, in the last about 5 years. But the key is the word deflation. Just because it's advancing doesn't mean that it's actually gaining the thickness. So even though it's still covering a larger area, it's not as thick as it was. I give this example in my class. It's like Play-Doh. You have that little container of Play-Doh, you pop the lid open, the Play-Doh's that thick, that big around. But if I sat there patiently long enough, could I cover an entire classroom desk with that one container of Play-Doh? And the answer is yes. It'll be a very thin layer, but I'd cover a huge area. And that's what's happening in most of these cases, is that overall, we are seeing a decrease in overall mass. Some areas we do see some exceeding in growth in surface area, but the mass or the volume of that ice is depleting rapidly. And that will complete part A. So part B is called Glacial Erosional Landforms. So we'll be able to split this up within the lab between erosional and depositional, but let's start with this. The first thing first is QR code. Definitely check that out. It opens up a Google Earth link that takes you to a website where it actually drops you down so you can see a landscape that has been eroded by glacial landscapes. This location in particular is the Devil's Post Pile near Mammoth, California. And what's really impressive is as you kind of move around and look down at that basalt that had been abraded and cleaned and polished by glacial ice, you can actually identify striations or scratch marks on top of that surface. So again, looking at types of erosion, these are some of the features that are most prominently observed after glacial erosion. Things such as glacial striations, troughs, cirques, hanging valleys, arêtes, cols, horns, and truncated spurs. As you can see, we provided you very clear definitions for each one of those features, because with these features and more, you are going to identify these on this beautiful drawing that's been presented for you. This is a classic black and white sketch of a glaciated topography, and your job is to identify at least one of each of those features on the previous page. Now, what's interesting about this and something to think about is that there are lots of right answers. So, just because your answers might be different than the person next to you or a friend that's working on this lab along with you, that doesn't mean it's wrong, because there are multiples of each of those features found on this diagram. Only find one. Don't get too crazy with all your lines. But remember, there are wrong answers too, so make sure that you're very clear as to what you are identifying as being that specific feature. Now, moving forward to question 7, for each of these 4 photographs shown below, identify the most prominent glacial erosional landforms. So you're moving from a drawing into actual photos of what these features would look like, which I think is wonderful, because you're then able to observe just the sheer size of what these features look like in your landscape. So moving on to the next page, we can see that we will begin part C. So part C is called glacial depositional features. So now we're looking at features that were caused by deposition. So one of the most common things that you're going to observe out in the field are called erratics. Erratics are very large boulders and rocks that were dragged by glaciers and erratically placed within the landscape. Other things that can be observed are sediments. So it says here, the sediment and material resulting from glaciation can be categorized in one of 2 families. The very, very, very fine grain material can be called glacial flour, and when it's wet, we call it glacial milk. It's so fine that it actually works as a polishing compound, and as that glacier is moving along and using that very fine glacial flour, and it smooths and polishes the surfaces. The other type of material, which is quite a bit larger, is called glacial till. Till is any material moved and deposited by a glacier, really regardless of its size. But usually when we identify till in the landscape, it's going to be observed as moraines themselves. So a great example, here we are. QR code, scan that with your phone, click the link. It takes you to Olmsted Point in Yosemite National Park, and it gives a great view of the north face of Half Dome. You're also going to be able to observe some glacial deposits at this point. And I just think that's a great way to observe, again, these real things out in the greater landscape. So question 8 says, review the following definitions, and then we're going to plot them kind of like we did in part B. So down below we have all these different types of definitions of features themselves that are depositional. So we're going to have moraines, and there's different types of moraines: terminal and lateral, medial, and recessional. If you need additional help with this, now that I'm kind of mentioning about it, I have some great videos that I've shared within the description of this. I've got a field trip video to Lake Sabrina in California where I point out some features and how they're made, as well as check out some of my other lecture videos that I've got. I've got several hundred videos that are on YouTube that help, all of which help define some of the features and ideas found in all of these labs. So moraines, real quick, I just want to explain that one because I think it's a little more challenging. Imagine the glacier is working very much like a bulldozer would, and as it's plowing through and moving all that material, you're building large ledges found at the end of your landscape. Well, those large hills or piles of material are made of what we call glacial till, and therefore they're considered a moraine. Again, you have drumlins, eskers, kames. Within these definitions that have been provided, you're going to be able to identify them here on this drawing, on this landscape. Once you complete that, again, I love this idea. Label an end moraine, a lateral, and a recessional moraine from this alpine glaciated photography that has been provided within this exercise. So this is a real life location. Can you identify any of those features? And just for the fun of it, do you see any other ones that we've talked about already? Do you see perhaps a horn or arêtes or things like that? You don't need to label those, but always be on the lookout, because the more that you're able to become comfortable with identifying these features, the easier it will be on exams to find them. Well, that being said, that'll wrap up Part C. So Part D is called Glacial Lakes. Now, we've talked about erosional and depositional features, and one more set that we need to discuss are the lakes themselves. Now, it says down here that lakes are common features in glaciated environments. A lake that is confined to a glacial cirque is known as a tarn. Tarns are common in areas of alpine glaciation because the ice that forms a cirque typically carves out a depression in bedrock, which then fills with water after the glacier is gone. So then moving forward into this next part, we can check out one of my favorite stops along the eastern Sierra, Lake Sabrina. Lake Sabrina is a tarn nestled in the Sierra west of Bishop. So then again, take a photo with your cell phone, click on the hyperlink, and we'll be transported to one of the most beautiful spots along the eastern Sierra. From that video, you'll be able to spin in 360. You'll be able to see the tarn itself within the cirque, arêtes and horns. And if you were to even travel a little bit farther eastward from that location, you'll be able to observe some moraines and erratics. So question 10 down here says, review the following definitions of the different types of glacial lakes. So you've got tarns, paternoster lakes, kettles, and moraines. And for this one, you're actually going to go back on figures to 18.6 and 18.8, both shown earlier in the lab, and you're going to identify some of these types of lakes in those features in those diagrams. So once you've completed that, that will wrap up this part of the lab, and we'll be moving on to Part E. Welcome to Part E, a case study on the Taku and Norris glaciers based out of Juneau, Alaska. I think one of the best ways to just observe glacial advancement and retreats is by utilizing genuine case studies that have prolonged data, going back to the 1700s up to present day, of seeing how advancements and retreats of these glaciers have operated. So what we're finding is that this glacial area in Juneau, Alaska are known as tidewater glaciers, meaning essentially they're the type of glaciers that are extending out into oceanic waters and then can calve off and turn into an iceberg. So we're able to observe a lot of information that's been provided here. The first step is here we have our classic QR code and hyperlink. Take a photo, click the link, and you will be transported to this region so you can observe some additional information and resources that you can see. And then we move on to question 11. Question 11 is referring to the diagram on the next page, which is essentially a topographic map with contour lines of elevation, as well as contour lines showing the extent of these glaciers at certain times in history. So question 11 takes you step by step, asking very specific questions, having you color, identify, draw a line, do a measurement. So it's asking you a bunch of different parts, which is essentially creating your case study based on this diagram here. So this map I put together showing these three glaciers based out of Juneau, Alaska, and it's having you represent and identify different things, filling in the legend, looking at the extent of the Taku Glacier in 1963 maybe, or things like that. So this is a great way for you to make reference as to what the region would have looked like and what it has looked like. Then those big thinking questions talking about, because again, these maps are only expressing advancements and retreats. It's not talking about the mass or the density or thickness of these glaciers, because it's going to ask some questions. And think about it. Why are some glaciers advancing? Why are some retreating? I mean, we're limited to this box as to what we can see. What is beyond this box? So perhaps it might help you to open up Google Earth Pro or looking at Google Maps and visualizing this place, but from a different scale, so you can observe what's farther up within these canyons and valleys themselves. Once you complete those questions and have evaluated your case study and wrapped up your final focus question, you would then complete this part of the lab. So let's move on to the next letter. Welcome to the final part of this lab, Part F, Glaciers and Sea Level Rise. So as we've learned so far, we have seen features that have been caused by erosion, deposition, lakes. But what about some of the greater elements? We've learned that glaciers are reservoirs of stored fresh water. We've observed changes in our climate or long-term weather, and in conjunction with these changes, we have documented a dramatic loss of ice across the globe. What does that mean for those of us who live along the coastline? Well, this table right here, figure 18.11, is utilizing satellite data showing the average rate of change of sea level rise. So we can see that on average it's about 3.3 millimeters per year, which, I mean, on a small ruler like this, we're talking about just 3 of these little bitty lines every year. Well, question 12 has you evaluate that, saying, well, assuming that it's on average 3.3 millimeters per year, how much or how more will the sea level rise over 30 years? And you'll multiply that out, be sure to show your work. Then you're going to convert that into inches, and you're going to see that these itty bitty little millimeters add up over a long course of time. Now, besides this information, the National Oceanic and Atmospheric Administration, NOAA, has put together an incredible resource that's online, and that's what the remaining part of this activity is going to take advantage of. So what you're going to need to do is either scan the code or click the hyperlink to access the website. I find this to be better done on either a tablet or on a desktop or laptop. But the website itself is called the Sea Level Rise Viewer, and it's a really interesting resource because it's North America, most of North America. I think there's parts of Canada that are not included. But what it does is it shows, based on the trajectory of current sea level increase, what areas will be affected by sea level rise, and you have a little bar on the left-hand side where you can raise and decrease sea level and see what areas are being affected. So as an example, it takes you step by step. Step 2, after you open up the application. In the search bar, type in Huntington Beach, California. Then it will zoom you into Huntington Beach. Step 3, move to the north and northwest on the map to view a little blue water droplet pinpoint and click on it. It should be the Sunset Aquatic Park. When you click on it, a little photo of the park will pop up. On the left-hand side, you're going to see an adjustable MHHW, which means mean high water, or using high tide water levels, and you can move it up and down through different, 10 foot, 15 foot, 20 foot. So you'll follow these directions, and you're going to be able to observe certain areas that will be dramatically affected by sea level increase. Now, obviously, we're not talking about a catastrophic event where all of a sudden everything shoots up by 10 feet. What we're trying to explain here is that even with your mathematical numbers that you computed looking at the previous part of this lab, over short periods of time, 10 years is not a long time. How far will sea level increase and what areas are going to be affected? You're going to be able to check out a couple different areas such as Corpus Christi and stuff like that across the United States. And you're going to be able to then zoom out and just look at the overall changes. People who don't live along the perimeter of the United States will not see a great change for themselves. But some areas are very, very flat, and they're going to see dramatic flooding, dramatic changes. And this is really a genuine concern for not just the people and the communities that live there, but even just for the resources. What are we going to have to do to prevent these entire cities from being flooded or being completely submerged by several feet of water if things are not done? Well, I hope this was helpful. I hope this allowed you some opportunity to reflect and to understand when we talk about just sea level change, when we talk about glacial environments, that these are really big, prominent pieces of Earth history and things that we deal with on the day-to-day basis. Again, ice is an incredible reservoir of stored fresh water. If we lose that ice, we run out of our genuine storage of fresh water. Here in California, specifically Southern California, a majority of our fresh water, it comes from the snowpack of the Sierra Nevada. If we don't have snow, we don't have drinkable water, and we're going to have to use reclaimed water, which most people don't want to even talk about. This toilet water that's been cleaned that we can then consume. I'd rather stick with the snow, so let's make some right choices so we can stick with that type of a resource. I hope this was helpful. For many of you, this will be your last lab and the last time that I see you. Again, comment below if you have any questions. Be sure to like this video, and please subscribe to check out some of my other content. I hope this was helpful, and I really do look forward to seeing you out in the field.